After the preliminary discussion of the first reaction, now I will derive three particular reactions and I will derive the values of relaxation time. So let me start with the very simple reaction, then of course slightly complicated and then more complicated reactions. So I am taking the simple reactions. A is equal to B A is equal to B. Because if you understand the simple reaction, you can solve any complicated type of the reaction because the methodology is exactly same. So this is K1 is the forward reaction and this is the backward reaction. Suppose I am using the T-jump method. Okay. Just like the normal kinetics. Forget about it is a fast reaction. So basically, naturally, there must be some initial concentration. And after the time T, X amount of B is produced. So if I want to calculate the rate, so it is just like very simple. dx by dt is equal to K1 A minus X, because initial point is A, after the time it is converted, minus K inverse 1 and the concentration is X. So what I can write? I can write K1A minus K1X minus K1X. So I can write like that, K1A minus K1X. Better to use the same color. So this is our first reactions. Now I apply the relaxation kinetics term, that as I told you, it is a time, this is starting point, reaction is going on, suddenly there is a change. So it is XE, this difference is delta X, and this is the relaxation time I have to calculate. So second equation is that from X, it is new equilibrium, and suppose that is equal to delta X. So I can write like that, X is equal to delta X plus XE. So you can write it is equation 1, it is equation 2. So like that. Last step. Very simple. If you understand, you can solve any complicated reaction for the relaxation time. Because for solving any numerical problem, your concept must be clear. Otherwise, you are not able to solve any numerical problems related to the fast reactions. So third equation is very simple, because once there is a change in equilibria naturally, so at equilibria, this equation is available in the any books. So at equilibria, so now system is like K1 A minus XE, equilibria, like that, minus K1 XE, again equilibria. So what I can write? Shortcut, K1A is equal to K1 plus K inverse 1 XE. That is our third equation. So let me solve. What I will do? I have to substitute first value of X. I have to substitute value of K1A in this equation. So you will get the final results. How? Okay, let me write from here. Okay, I can write right here. So K1A, of course, dx upon dt is equal to minus K1 K inverse 1 delta x plus xe. Last step, value of k is equal to K1 plus K inverse 1 xe minus K1 K inverse 1 delta x plus xe. Very simple. K1 plus K inverse 1 xe, cancel with K1 K inverse 1 xe. So what we will get? What we will get? You can understand these things. I can write like that, K1 K inverse 1 xe. What I can write? K1 K1 xe, then minus K1 K inverse 1 delta x. So delta x upon dt is equal to minus, why minus? Because here is minus K1 K inverse 1 delta x. Just to remember your first order kinetic system, and as because now we are concerned about these small changes, just you see these things, and I have to calculate the time required to just from perturbed equilibrium to that equilibrium. So now I can write that d of delta x dt is equal to minus K1 K inverse 1 delta x. Last step, rearrange this equation like your first order kinetics. Rearrange the equation for the integration, same thing, nothing new. So like dy dx by x like that. Equal to minus k1 k inverse 1 dt from 1 to 2 like that, 1 to 2, like dx by x, natural log of x, 1 to 2, x2, x1, t2 minus t1. So kinetics is exactly same, whether it is the fast reaction or the slow reaction. At the starting point, so t1 is equal to t2, it is suppose 0 condition. So what I will write? Natural log of delta x and x0, 1 and 2 like that, is equal to minus k1 plus k inverse 1 t. Now this natural log delta x and x0, where is here actually, this is actually delta x divided by e like that. That means you know all these things, that natural log of dx by x0 is maybe 1 or dx by x0 is exponential. So what I'll do, delta x anti-log of x0 exponential minus k1 plus k inverse 1 and t. Just to see this first formula, a is equal to a0 exponential minus t. Now this distance, so here is tau value is equal to 1, I have just k1 and k inverse 1. So this is tau value. So what I can write? What I can write, that delta x is equal to delta x0 exponential minus t by tau. Because tau is equal to, this is actually relaxation time. So time or the distance between this part of equilibrium to that equilibrium, so that is called the relaxation time. Now I am coming to this some complicated system. Then you can understand that what is the difference between these types of the reaction. So now if you see carefully that I have not used any complicated system. It is just like your first order kinetic system. A is converted into B. Only thing is that here we have used a new term, that is called the relaxation time. So every time we determine the relaxation time on the basis of these things. So now I'll solve another system, then you can understand. Then अब बैठ सकते हो, अब बैठ जाइए, क्योंकि अब तो written है पूरा. Now the last system or second system or third system, time permits, I will do this third system, but first I will solve the first system. A is converted into B plus C. Also again it is a T-jump system. Or just to imagine water H OH. Just for again same system, K1 K inverse 1. What is the difference? Difference is that initial condition is A, no problem, but there are two reactants. So naturally, and first case when A is converted into B, there is only one reactant, so only X is there. So here is 2, so this X, that is the difference. So just like your same thing, nothing new, dx upon dt, is equal to same thing, K1 initial concentration is A, after the time T, of course 10 to the power minus 6 second. So minus 6, you can, in some books you can write A0 also, no problem. You can write A0 initial concentration, but for simplicity I am using simply A. Here, because there are two, and for this system, I am not saying that the concentration of H and OH will be different, but for the water system, you know that hydrogen concentration is 1 into 10 to the minus 7, hydroxy ion also 1 into 10 to the minus 7. So therefore, I am using simple X. Otherwise, concentration will be different. K1 X square. Any problem? In first system, there is only X, here X square, because there are two reactants. Okay. So what I can write? Just like your first system, K1A minus K1X minus K11X square. It is up to you. You can write like that. X is common, K1 plus K inverse 1X. That also. Or same thing, there is no difference, change, same thing, nothing new, X. Only fundamental concept is same, but the reaction is different. But in that reaction is also, the reaction is going on steadily, suddenly you disturb that equilibrium, so X converted into Xc, same thing. So there is also X, Xc, so delta X. So here you can write X is equal to delta X plus Xc. Same, just like your first system. So you can write here, or I can write this side also, so that I can write here also. So we'll get more space. So dx and dt is equal to K1A minus K1 Xe plus delta X, no problem. You can solve, if you are a mathematics student, it is up to you, you can solve it any system, but I want the final equation should be correct. Minus K inverse 1 X square delta X plus Xe square. Any doubt? So there are two equations. First is this, second is this. This is the simplest method. You can, now there is a change in equilibrium, so you can write that at equilibrium, so K1 A, like that, first system, minus, sorry, K1 minus Xe, because it is equilibrium, minus K inverse 1 Xe square. In place of X, after equilibrium, now it is Xe. So therefore, so I can write like that, K1 A minus Xe minus K inverse 1 Xe square. So what I will write and then solve it. by single method. So is equal to same color. So K1A is equal to, suppose K1A is equal to, I can write like that, K1, if you don't understand, I'll again write XE, XE. You follow my point? What I can write? I can write K1A minus K1XE minus K inverse 1 X square. Just take the common of the XE. So it is. What now I'll do? I have to substitute the value of K1A in the equation number 1. So but before that, what I'll do, I'll solve this part also. A plus B whole square. Again, it's very simple mathematics. A square plus B square plus 2AB. So nothing new. So what I'll do is this. So delta x square plus x e square, a square plus b square, 2ab, 2 delta x and x e. Any doubt? So just you substitute this value here first. So last step, final step, in place of, I'll write like that. For student simplicity, I'll just elaborate it. K1 XE plus K inverse 1 X E square, right? Minus, I'll solve it, K1, it is just a substitution thing, nothing new, minus K1 delta x, again minus, this actually is very small, so this part can be, I will not write these things. I eliminate the K1 inverse 1 delta x square, but I will definitely write K inverse 1 x e square, minus, because here is minus, minus 2 K inverse 1 delta x x. Agreed? So K1 XE, K1 XE, K1 XE square, K1 XE square. So there is only two things, one is this and this. Just you take 2 minutes so that you can understand these things. Again I am saying it is simply simple mathematics, and you will get the final result. Our objective is to determine the relaxation time. Have a patience so you can solve it. So what I will do, I will remove all these things so that final formula can be determined. Okay, so let me write last step. D, again dx, because there is a change. Same thing, just like you think for first system. So minus K1 delta x plus, sorry, minus 2 K1 delta x and xe. So again minus delta x is common, so yellow color, K1 this plus 2 K inverse 1 XE. Normal integration for to know the system. Rearranging the system, d by dx on dx integration minus k1 2 k inverse 1 xc dt. You know, this is 1 to 2, this is also 1 to 2. So, natural log delta x2 delta x1 minus k1 2 k inverse 1 whatever the concentration. T2 minus T1 like that. So it is, if I write when T initial condition T 0, so delta x, just to compare with the first system, normal cases, same thing, delta x 0 log exponential minus k1 2 k inverse 1 xc t. So what would be the tau value? Anybody? Yes, 1 upon first case, just you remember 1 divided by k1 plus k2, that is the tau value. Here it is k1 plus 2, just to compare with your first system, this is the tau value of the system. So I can write like that, due to the shortage of x, delta x0 exponential minus t tau. So just now I compare with your first system. What I am doing, green color, so that you can understand. First is that A, B, tau value 1 divided by k1 k inverse 1. Okay. Second, A is equal to B plus C, tau value 1 k1 2 k inverse 1 xe. Third, it is your homework, that H2O converted into H plus O. No, sorry, I have already solved it. Now third value is A plus B is equal to C. That means H, it is your homework because time is not there. You follow my point? If you understand this system and if you solve it, you will get I'll just write a big way, so that tau value is equal to 1 k inverse 1 plus k1 concentration of A, suppose two systems of A, concentration of hydroxide ion is B. So now you have seen what is the message, take home message is that relaxation time can be calculated without any problem, but it depends upon the forward reaction as well as the backward reaction and the types of the reaction. Here I am using A converted into B, system is same, I am getting this type of value. For A, B plus C, I am getting K1 divided by K1 to K1. X1 you can write A also, that means initial for hydrogen and hydroxyl ion it is same, 1 into 10 to the power minus 7 like that. Today due to shortage of time I am unable to solve any numerical problem. For third, it is homework, because if you understand the first system, and so you can, I hope that you will definitely solve this system. But only thing is that there, if it is write H plus OH, so you have to write A and this concentration is B, so it will be A minus X as well as the B minus X, and that is X. You follow my point? So you will get 1 divided by K inverse 1 plus K1 A plus B. So thank you very much. Thank you.